Hello everybody. I promised in the previous video that I'm going to explain in more detail how to communicate with the robot using the real-time data exchange. This will be a long video. Maybe I will separate it to few smaller videos. It's definitely for more advanced users in terms of the tools we are going to be using, but let's go straight into it. So it is recommended that you watch the videos that I made previously about how to download the basic packages that are needed. So for this tutorial we are going to need the folder called RTDE. You can see it over here on the left side, which contains different scripts provided by the universal robot. Again, I think in my first video on RTDE communication I explained how to get it and how to set it up. So as we can see over here, I have also an example control loop. This is another folder that comes in that package. This is an example provided by your robot company, and I actually went over it last time as well, so I'm not gonna go over it anymore. In this video, what I would like to do is I would like to focus on explaining how to use Servoj command. Servoj command is one of the commands that's non-blocking command. What does it mean? For example, if we want to move from one point to the other using standard UR5 functions that are available to the user, we can use move L, move J, move P, and they are going to move us to the point, and that's it. Meaning, let's say we want to move from one point to the other, from the second point to the third, from the third to the fourth. In order to have a smooth continuous motion, this is kind of impossible with move L, because at each intermediate point we are going to stop and initialize the motion again. So the robot will not move in a smooth fashion. So Servoj is an example of a command that's not blocking, meaning we feed the Servoj with values at each time step. In the case of real-time data exchange, it is every 0.002 milliseconds, meaning every with the frequency of 500 Hz. So it is important to send the values the correct frequency, otherwise we will not be able to use this command. So I'm going to attach all the code on my GitHub, so you can download it, play around with it. I just made this code real quick so you can understand more or less how to do it, but again, this is a good starter for you. You can experiment, you can see what is the best way, what are the best parameters that will work for you. So let's just go straight into it. So we have here folder YouTube, and we are gonna need the RTDE folder that I mentioned before, the control loop configuration XML, which I also talked about in my first video. This basically tells us what registers are we going to use to read and send values to the robot, as well as the measurements that we are interested in taking. So in our case it's going to be TCP pulse and TCP speed. I also have defined some other measurements which I do not use, but that's not very important. Another two files that we are going to need is minimum jerk planner translation file and minimum jerk Servoj. So minimum jerk Servoj is our main file from which we are going to communicate with the robot, but it strongly depends on the file called minimum jerk planner translation. So let's go over this initially. It's not related to UR5 itself, or in general UR. It's related more to motion planning. So I highly recommend that you Google trajectory generation with a minimum jerk trajectory and read, as you can see over here, a really nice explanation about what is this kind of trajectory, why is it called minimum jerk, and what are the properties and characteristics of this kind of trajectory. But basically what we have for X, Y, and Z, we are going to have some polynomial that describes in what way our robot should move. I'm not going to go into details over here. You can read more about it. Just Google minimum jerk trajectory. There are a lot of really good resources about that. So we are going to implement over here a class that basically at each time step creates a point on our trajectory. So how does it work? We have our initial pose I remind you that the pose is XYZ as well as RX, RY, RZ, which are the which is orientation of the end effector in the axis angle format. So this is the initial point from which we start. This is the final point to which we want to get. We have also the total time, meaning in how much time do we want to use in order to get from one point to the other. And later on you can analyze the code. Basically I divide the X, Y, and Z of the initial pose and the final pose, and I create the polynomials that are described in the article online. So we have the trajectory for the position. Again, this is a function of time, so in order to get the velocity we just need to take a derivative with respect to time. So we have velocities and we also have accelerations, and in this way, it's a very simple code. It's using just simple polynomials. We can create a trajectory which is very easy and fast to use. Again, this is trajectory just for the positions. I did not implement minimum jerk for orientations because it's more complex, and for now I think it will be good enough for our use. I also provide here a very short example. Again, initial pose that we read from the robot, the final pose to which we want to get, the time that we want to spend to get from the initial to the final pose. So let's run this code so you can understand a little bit better what we are talking about over here. Just 1 second. Here we go. So we can see here, if you look on the top, the X position from which we started was 0.33. If we look at the blue graph, 0.33, this is where we start. We have a really nice smooth motion to 0.95. And again, the same is for X, Y, and Z. Then if we look at the plots of velocity, what is really nice, and it's also very functional for our robot, as you can see, the initial velocity and the final velocities are 0, which is very important because we do not want to have abrupt beginning of the motion or end of the motion. We want to have a smooth trajectory, smooth motion of the robot from the beginning to the end point. If we look at the accelerations, also the acceleration starts at 0 and ends at 0. So we can see that the trajectory is really nice, it's smooth and follows the theory that's described on the website. So this is the kind of trajectory that we expect to get. So now let's get into the code and talk a little bit about how we can implement it on our robot. So we go into the file called minimum jerk Servoj, and we import the time, matplotlib for plotting, and the minimum jerk that we implemented in the other file. The name of the file is minimum jerk planner translation, and the name of the class is path plan translation. Over here, the functions, those are functions provided from Universal Robot. So we can see, because we are only using 6 registers, we read from we only write the 6 registers 0, 1, 2, 3, 4, 5, and over here also for changing the list to set point we only again use 6 registers. The beginning of the communication, I talked about it before. Here what is important to see, that because I moved the control loop configuration XML file to the folder in which I'm working right now, it's enough to just call the name. We do not need to enter any different directories. So here this is a standard code. That explanation you can read about, or you can just see the first video that I made about it. So I'm not going to go into detail. But again, the key over here, what we are trying to achieve, we want to use Servoj to move the robot from one point to the other. Servoj works by sending joint commands to the robot. We send joint commands which the robot should follow at each time step, and the robot has its own internal controller. If you are familiar with the concept of PD control, this is exactly what is happening. The gains of the P and D parameter we can control. The P parameter is called gain. If you go to the your script manual, you can also see more explanation over here. So we have Servoj, we send the join values at each time step. The time step we will set is 0.002 seconds. And we have the two parameters, look ahead time and gain. So the gain is the P term in the PD controller that has certain boundaries from 100 to 2000. And we also have look ahead time, which also has certain boundaries given over here. It's moving the trajectory and it works like a D parameter in the PD control. Again, PD control is very famous way of controlling robots and systems in general. So you can find a lot of information about how to tune those parameters and just in general about the intuition behind choosing the parameters. So going over here, this is standard procedure. So this is basically standard procedure that happens every time you want to run any code that you want. Here is the important part. I don't want to make the video too long, so I will talk about this. I will start from this point at the next video.